All right. Good afternoon. Uh, anyway, we've been looking into rational expressions and various types of methods for solving quadratic equations, and we had left off with rational expressions, and there was one other kind I was going to go into, but we were a bit pressed for time. And for what we have in terms of the types of equations we have, we left off with those that have rational expressions involved, and within that particular family, okay, we have what are referred to as proportions. Okay, and basically proportions are statements of equality that exist between ratios, and we have just for what we have regarding proportions. Okay, and we have as a rule of thumb. Okay, say if you have two ratios equal to each other, like we have that A over B is equal to C over D, then what you're going to have is that we're going to have another statement of equality on a particular set of conditions. Okay, and we have what are referred to as proportional cross products, where you're looking at multiplying alternating numerators and denominators, like you have A times D is going to be equal to C times B or B times C. And that is true as long as we do not have zero denominators. Okay, so this statement is going to be true on the basis that we do not have a zero denominator. So this will be where B does not equal to 0, and also where D does not equal 0. And now, and again, okay, now one might ask, okay, well, if B and D are 0, well, A times 0 is 0, and 0 times C is also 0. But the reason you have these restrictions is, again, we're starting out with rational expressions, and again, you can divide into 0, but you cannot divide by 0, that is, have 0 at the bottom. And just as an example of a proportion, and we can say, for instance, okay, we are looking at solving for x. And we'll have just a proportion where we have 2 over x plus 4 is equal to 1 over x minus 3 and we have just, in the case of identifying the restrictions, again, so we have that the denominators cannot be 0 in value. So we have the x plus 4 cannot be 0. And so we have the x cannot be negative 4. And also we have x minus 3 cannot be 0. So we have the x cannot be equal to 3. Okay, so we have just for the restrictions. Just to restate, so we have the x cannot be negative 4, and the x cannot be equal to 3. And just looking at what we have with our proportional statement. Okay, so if we take cross products, that is proportional cross products, so we have 2 mapped with x minus 3 and 1 mapped with x plus 4. So we have here just multiplying, so you have 2 times x minus 3 is equal to 1 times x plus 4. And we have, in following through, so you have with distribution, so you have 2 over x minus 3. So this will become 2x minus 6. Then we have 1 times x plus 4. And here we have the formation of a linear equation with like terms on opposite sides. So what I can do here, if I work with the variable terms, okay, so I can join the x's. In this particular case, we have 2x and x. I'm going to take out the smaller variable term in this case, which will be at x. Thus we have 2x minus x becomes x. And we have x minus 6 is equal to 4. And with x minus 6 equal to 4, if I add 6 to both sides, and we have an apparent solution with 10. And so we have x equal to 10, and we have the restrictions that x cannot be negative 4 and x cannot be 3 to be satisfied. And you can also check out, now we have 2 over 10 plus 4 is 2 over 14, and 2 over 14 is reducible to 1 over 7. And guess what? To the right, we have 1 over 10 minus 3, also at 1/7. Okay, so the value of x that would make 2 over x plus 4 equal 1 over x minus 3 is going to be at 10. Okay, now, in looking at what we have from the group of problems, okay, on page 69, okay, and we have, again, equations that involve rational expressions. And for what we have in the group, and we have from number 68, and we have the equation in terms of the variable t. And for this setup, we've got 1/3 minus 4 over 3t and that is equal to 7 over t. Alright, and just to sort of mention, okay, now we're dealing with an equation, so I want to get the fractions out, and just some things to mention. Okay, so to prevent a zero denominator, okay, we're going to have a restriction that 3t and t cannot be 0. Okay, 3t cannot equal 0, so t can't equal to 0, and have ditto t cannot be 0. And for what we have in our statement, okay, now we have the least common denominator, and the smallest term that all of 3t and t will go into, okay, well, that is going to be 3t. Alright, and again, I'm not going to write all the expressions in terms of 3t. I'm just going to clear out the denominators since I'm looking at an equation. Okay, if I had just rational expressions to combine, no equation, I would have all these ratios in the form where the denominator is at 3t. Okay, but since I'm working with an equation and trying to solve for t, okay, what we have here, if I multiply by the least common denominator, okay, so I have 3t times 1/3, okay, we have minus 3t times 4 over 3t. And we have is equal to, and again we have 3t times 7 over t. Okay. And so for what we have in our expressions, okay, so what's going to happen here, and you can go ahead and reduce. I'm just going to kind of just take this. Again, so you have 3t over 3 minus 12t over 3t is equal to 21t over t. And again, you can reduce in advance. So you got t minus, okay, and we have 12t divided by 3t is going to be at 4. 21t over t is going to be at 21. And so we have t minus 4 is equal to 21. And so we're going to have here that upon adding 4 to both sides, okay, we have t by itself, and 21 plus 4 comes out to 25. And so this satisfies the restriction that t cannot be equal to 0. Now, for what we have in the next item, for number 74, okay, this time we're going from the variable t to c. Okay, and here we have 2 over c plus 3 minus 1 over c minus 3, and we have is equal to 10 over c squared minus 9 and if I were to write this last denominator in factored form, okay, so c squared minus 9, okay, this is going to be a difference of squares. And taking what we have here, so we have with our denominator factors, okay, so we have, again, we have that c plus 3 and c minus 3 cannot be 0. Okay, so we have our restrictions that c cannot be negative 3 and that c cannot be equal to 3 either. And for what we have in terms of the least common denominator, again, I'm dealing with an equation, so I want to clear the denominators out. So least common denominator, okay, we have with quantity of c plus 3 times that is c minus 3, and if I distribute throughout what we have in the equation, and again, if you see the reduction in advance, okay, that's all right. And you have to be careful with the negative signs. Okay, so just taking what we have now. Okay, so we have with 2 over c plus 3. Okay, so here, okay, we're going to have c plus 3's to go out. And with c minus 3, okay, c minus 3 is going to go out. And for c plus 3 and c minus 3, we have these to go out completely. So for what we have in the steps, you have 2 times the quantity of c minus 3. And we have minus, okay, we have the quantity of c plus 3 times 1. And it's with this second set of terms I said that I'm referring to being careful about the signs. And we have with what is to the right case, so you have 10 left over. And working with what we have now, so you have 2 times the quantity c minus 3, so this would be 2c minus 6. And distributing subtraction, kind of like distributing negative 1 over the quantity of c plus 3. So we have a minus c and a minus 3. And we have is equal to 10. And we have, and then gathering like terms together. So you have 2c minus c to become c, and negative 6 and negative 3. Okay, so this will be minus 9. We have is equal to 10, and if we add 9, okay, to both ends, okay, so if c minus 9 is equal to 10, okay, we have that c is equal to 19. Okay, so on the basis that the algebra is done correctly, which it is, okay, we have c is equal to 19, and both restrictions, that c cannot be negative or positive 3, okay, will be satisfied. So there is one value of c for which this equation is going to ring true, and that's kind of like it's on conditional And the condition for this to work is going to be where C must be equal to 19. All right, now for what we have in the case of number 80, okay, this one, a little bit of a trick one. And we have for the setup here, okay, so you have 4C all over C minus 5, okay, and we have minus 1 over C plus 1. And we have is equal to 3C squared plus 3. And we have all over the product of C minus 5 and C plus 1. Okay, so I'm just going ahead and displaying everything in factored form. And now, just taking what we have now. So we have the denominators. Okay, it's C minus 5 and C plus 1. And, okay, so we have with the restrictions. Okay, we have that C minus 5 cannot be 0. And C plus 1 cannot be equal to 0. So if C minus 5 does not equal to 0, well, we have that C cannot be 5. And if C plus 1 cannot be 0, well, we have that C cannot be negative 1 as a consequent. Now, for the least common denominator. Okay, least common denominator, okay, this is going to be the product of C minus 5 and C plus 1. And just multiplying, okay, all the expressions out by the least common denominator. Yeah, the process is a little bit painstaking, especially when you're trying to sidestep from any potential careless mistakes. So we have for the next term bring down subtraction. And here we have the quantity of C minus 5 times that of C plus 1. Okay, have times 1 over C plus 1. And distributing the least common denominator over the last ratio. So you will have just the numerator will be left over at this end. Okay, so you have for the first set of terms. Okay. Yes.
Where did the 3C squared come from?
Okay, that was
Oh,
that was
no.
in the original setup. That's yeah.
Oh, okay, never mind.
Uh huh. Okay, so you have for the you got for the first ratio. Okay, so you have multiplying by the least common denominator. Okay, so C minus 5 will cancel out. And we have for the next, okay, so we're going to have C plus 1 is going to cancel out. And then we have with the last ratio both C minus 5 and C plus 1 are going to clear out. So for what we have left standing, okay, so you have C minus 5's canceled each other. So we have, so you got 4C and C plus 1. We got the subtraction. Now we got the quantity of C minus 5. I'm keeping the parentheses right now again because once you distribute subtraction, okay, both C and then minus 5 are going to be affected. And for what we have to the right, so we have 3C squared plus 3. And so we have looking at distributing. So you have 4C times the quantity of C plus 1. Okay, so this is going to be 4C squared plus 4C. And we have the next distribution. So you have minus C. Subtraction over negative 5 reverts to addition of 5. And so looking at what we have now, so we've got 4c squared plus 4c minus c. This becomes plus 3c. And we have plus 5. Again, we have equal to 3c squared plus 3. Okay, now we got a quadratic equation, but it is not yet in standard form. So I'm going to set this equation to 0. So between the c squared terms, okay, we have 4c squared and 3c squared. And I'll take the lesser of the two away. So we have minus 3c squared. Had that part taken out, and also take out 3. So you have 4c squared minus 3c squared, so this would be c to the second, plus 3c, and plus 5 minus 3 becomes plus 2. And we have is equal to 0. And looking at what we have upon factoring, so we have the quantity of c plus 1 times that of c plus 2 is equal to 0. And then looking at resorting to the zero product property. So we have c plus 1 equal to 0. And we have an apparent solution with negative 1. With c plus 2, if I set this equal to 0, we had that c is equal to negative 2. And if you notice, okay, we have c at negative 1, and going back to the restrictions, and guess what? We have c cannot be 5, and we have the c cannot be negative 1, and so we have because of this particular part, c equals negative 1. That is not going to work, and this will be referred to what is an extraneous solution. And what I mean by extraneous is that it looks like it's going to be a solution on the basis of the subsequent steps. However, in terms of the restrictions imposed from the get-go, that will affect what is introduced and what the outcome ultimately ends up as. Okay, well, this one does not qualify. But in the case of negative 2, for negative 2, so if it's the restrictions of not being 5 or negative 1, so that part is satisfied. So for number 80, there could have been up to 2 solutions, but since negative 1 did not fit the second imposed restriction, there's only one value that will work, and that is going to be negative 2. And again, for rational expressions, okay, we want to avoid zero-valued denominators. All right. Now, for what we have in the case of number 81, okay, and for this one, okay, so we're switching over to yet another letter, okay, and in this one we have with M, and this one's going to be a bit tricky too, because you're looking at what's going to be a development of a quadratic equation that is not going to have integer roots. And for this one, so we have in the variable m, okay, so you have m all over 2m plus 1 and we have plus 1 and we have is equal to 2 over m minus 3, okay, and okay, so you have two distinct denominators. Now you have for your restrictions, again, 2m plus 1 cannot be 0, okay, and in this one 2m plus 1 cannot be 0. If I move the 1 over, we have that 2m cannot be negative 1, So we have for first restriction, okay, we have the m cannot be the fraction -1/2. And for m minus 3, since that cannot be 0 either, okay, we have the restriction that m cannot be equal to 3. And in terms of the least common denominator, okay, that will be the product of 2m plus 1 and m minus 3. Alright, so if we clear out the denominators, so multiplying all the terms out by the LCD, okay, so we're going to also have a cancellation of 2m plus 1, and then just multiplying 1 by least common denominator. So we have terms that are going to be FOILed out. Okay, so we have for the first grouping case, so we're going to have 2m plus 1. It's going to go out. Then we have distribution for the second, in other words, FOILing out. And so in this setup, so we have m and m minus 3. And then if I FOIL out what I have here, so I got 2m times m, so this will be 2m squared. Outside product is going to be a negative 6m. Inside product we have plus m. Last product we have at negative 3. And then we have 2m plus 1 multiplied by 2. And so we have, upon distributing, okay, so you have m squared minus 3m plus 2m squared. And we have a negative 6m plus m, so we have a negative 5m minus 3. And we have equal to 4m plus 2. Okay. And just rearranging the terms and putting in descending degree order. Okay, so you have only squared terms we have are m squared and 2m squared. So this will become 3m squared. And then we have negative 3m minus 5m becomes negative 8m. We have minus 3. Again, we have equal to 4m plus 2. So we have a quadratic equation. And if I put this in standard form, again, just setting equal to 0. So I'm going to move the 4m and the 2 over by subtracting. So for what I'm going to have here is we have 3m squared. Negative 8m minus 4m becomes negative 12m. Negative 3 minus 2 becomes negative 5. And we have is equal to 0. Okay, and I'll go ahead and mention this is a trick one because this particular trinomial cannot be factored. And one reason for this is that if you try stuff like factoring by grouping, where you have, for your product, you have 3 times negative 5 is negative 15. And there are no integer factors of negative 15 that will add up to negative 12. You might think of negative 15 and 1, but the sum of that is going to be minus 14. Other combination with a negative sum would be negative 5 and 3, and that adds up to negative 2. But nothing that will add up in the integers to negative 12. Okay. And so for this one, Okay, we're looking at the use of the quadratic formula. Okay, and so we have for this particular setup, okay, now we're solving for m, not the letter x, but we're still going upon the same premises. So we have that a is equal to 3, and that b is equal to negative 12, and that c is equal to negative 5, again, we have with the quadratic, so you have negative b plus or minus the square root of b squared minus 4ac all over 2a. And being careful with the substitution, so you have negative b. Now b is already negative, so we're going to take the opposite sign of negative 12. And for b squared, okay, so you have the square of negative 12. We got minus 4 times 3 times negative 5 you have all over 2a, so you're going to have at 2 times 3. Okay. All right, and just to mention the numbers here. Okay, so for what we have inside the radical, okay, so I have negative 12 squared. This would be 144. Now, negative 4 times 3 is negative 12. Negative 12 times negative 5. Negative times negative is a positive, so that's going to be a positive 60. So right now we're going to have in the radical the number 204. So 12 plus or minus the square root of 204. And we have all over 6. Now for 204, again, not a perfect square number, but it is a number that can be reduced in the square root. Now for 204, okay, now 204, rather large number, but the highest perfect square that will go completely into it is only going to be 4. If you notice, got 4 times 51, and for 51, 1 is the largest perfect square that will go into this. So the square root of 204 reduces to 2 times, okay, the square root of 51. Okay. And for what we have here, now you can do separate modes of reduction. Okay, one approach. Okay, we've got 12, 2, and 6. 12, 2, and 6. So we have even numbered leading coefficients. And I'll show you just at least one pathway. So if I were to, let's say, factor out 2 halves. So like for 6, 6 will factor out to 2 times 3. And then we have for 2 into 12, that will go 6 times. And 2 into plus or minus 2 times the square root of 51. Well, the 2 is already factored out. And just for your compact answer, okay, we say we have 6 plus or minus the square root of 51 all over 3. But I'll mention this as well. Okay, so another possibility. You won't usually see this kind of notation, but if I were to separate, so you have 12 over 6, that goes to 2. And 2 6 reduces to 1/3. So you have square root of 51 over 3. So if I were to itemize, you have in compact form either 6 plus or minus the square root of 51 over 3. And if you were to separate, you would have like 2. Yeah, plus or minus. Now 6 plus or minus the square root of 51. That whole expression is all over 3. But here you have 2 is by itself and it's separated from the fraction. So 2 plus or minus the square root of 51 all over 3. Yeah, that was a bit of a trick one. And just for the numbers, the restrictions were that m could not be -1/2 or 3. And with these figures, I don't think I had to worry about violating either of the restrictions. Okay, so you have for this, yeah, very tough problem. And so we have a couple of irrational roots on this one. Now, in taking what we have with number 82, okay, kind of challenging but not excruciating like 81. And we have for this particular quadratic equation, so we have here, so you have 7 plus 20 over z is equal to 3 over z squared. Okay, so you have z cannot be 0, z squared cannot be 0. So to satisfy z and z squared from being 0 in value, we have that z cannot be 0. And for the least common denominator, in other words, the smallest term of both, z and z squared will go into, well, that's just going to be z squared. And just taking what we have now, if I multiply all the terms out by z squared, it's about 7 over z squared. I have plus 20 over z times z squared. I have 3 over z squared, okay, times z squared. And what's going to happen here, now you can go ahead and reduce. Let me do it like this. Okay, so you got 7z squared. Now for 20 over z times z squared, so I have z to cancel out, but I'm still going to be left with first order in z. And for 3 over z squared times z squared, you have complete cancellation of z squared. So again, z into z squared still leaves a degree in z. So here we have 7z squared plus 20z is equal to 3. And if we express what we have in terms of a quadratic equation that is in standard form, so we have 7z squared plus 20z minus 3 is equal to 0. And here, now if you can visually factor out, that's fine. And just on the side of factoring by grouping, okay. So I got leading coefficients, so I have 7 and -3. half equal to negative 21. And just taking what we have here, so we have with negative 21, we're looking at factors that will add up to 20. If you notice, we had 7 and negative 3. However, 7 plus negative 3 is only 4. And for what we have, okay, just to override, okay, so we have 7 and negative 3. And we have, again, sum of 7 and negative 3 is going to be 4. And if I make the adjustment, making the positive factor even higher, and the weight of the negative even lower, and guess what? We have 21 and negative 1. The product of 21 and negative 1 is minus 21. And we have 21 plus negative 1 comes out to 20. Okay. And so we're going to have this combination to check out. So in working with what we have here, and if I split up, and I could say either plus 21z minus z, or have it the other way around. And if I have a negative and a positive term, I like to have the positive term to come afterwards, and that's to preserve having the middle operation between the first and second pairs to be addition. Okay, so if I do it this way, 7z squared minus z, and you have plus 21z, not 20z. Minus 3. And looking at grouping together, so I have 7z squared minus z. Then we have the operation of addition in the middle. And we have the quantity of 21z minus 3. And for the greatest common factor, okay, so we have between 7z squared and negative z. Okay, so you have z. You have times the quantity of 7z minus 1. Bring down the plus. And the greatest common factor of these last two terms will be 3. And 3 into 21z minus 3, that is also 7z minus 1. So you have in the factors, we have 7z minus 1. And the other factor we have with z plus 3. Okay. All right. So reverting to what we have in this particular problem. So you have 7z squared plus 20z minus 3 is equal to 0. And we have with the factors. So you have 7z minus 1 and z plus 3. And setting each one to 0. So for 7z minus 1 equal to 0, I have that 7z is equal to 1. So we have that z is equal to 1/7. And for z plus 3 equal to 0, okay, we'll have that z is equal to negative 3. And again, just for the restriction, okay, we had that z cannot be 0. So our attempted solutions of 1/7 and negative 3 are going to be successful. So you have for this outcome, we have two solutions in z, one at 1/7 and the other at minus 3. Okay, now in the crossover, okay, and we're still going to be looking at quadratic expressions throughout, and there's going to be a little bit of a departure, I guess you can say, but still kind of going back to quadratics. And we're going to have, in the case of radical equations, okay, and to sort of kick things off, okay, with radical equations, okay, there's an item now, and this is going to be sort of a cousin of the square root property of equality, but it's going to be something that's going to be separate, and this is going to be what's referred to as the principal square root rule. And for the principal square root rule, this is going to state that the square root or any even root for that matter, and what I mean, you have like the square root, fourth root, sixth root, eighth root, so you have the square root or any even roots of an expression cannot reduce to a negative constant. Okay, and let me give you just a little difference here. Now, whenever we dealt with something like x squared equal to 36, and again the degree of 2, okay, you have possibly two solutions. And when we looked at the square root property of equality, okay, so you had, in this one, when we went from x squared equal to 36, say going from x squared to x, and we have plus or minus, okay, the square root of 36. We have x equal to plus or minus 6. And so you have with our combination, you had x equal to negative and positive 6. Okay. That's what you have with the square root property of equality. But in the case of what we have with the principal square root rule, okay, instead of starting out with x squared, if I had just x is equal to the square root of 36. Okay, so if you notice, you don't have x squared to start out with. We have x instead, and we have the x is equal to the square root of 36. Notice we don't have the transitioning like what we did in the second stage where we utilize the square root property of equality, because here we have just the x is equal to the positive square root of 36. And again, the square roots of an expression, that expression in this case being 36, cannot reduce to a negative constant. So any negative value, is going to be left out. So for the square root of 36, okay, that is going to end up at 6. And just another instance, if we have the x is equal to the square root of 100. Okay, now I know there are two numbers that will square into 100, but we're looking at just the positive square root of 100. And so in this case, x is going to be equal to 10. Okay, and this is where we have just the even root of numerical values in these cases. Now, let's say that if we were to branch out looking at solving for x, where x is part of the radical term. Okay. Now, say if we're looking at solving for x. Okay, so I have that the square root of x plus 1 is equal to 8. Okay, now, again, we have 8. Okay, that's a positive constant. And we have the even root with the square root. Square root of x plus 1 is equal to 8. 8 is positive. So we're at least going to have a solution. Okay, now, to get rid of the radical and thus free up what we have in x, we can undo the presence of the square root by squaring both sides of the equation. Right, let me just do a little bit of color coding here. So you have implicitly, we have with the square root, that's like the second root of a number. Okay, so like the square root of an expression squared, this will go to the expression that was in the radical. To the right I have 8 squared is going to be 64. Guess what? If x plus 1 is equal to 64, we're going to have the x is equal to 63. And so for what we have here, okay, so with x at 63, you can always go back and check. 63 plus 1 is 64, and the square root of 64 is equal to 8. And let's say that as another case here, and we'll change up the type of radical. If I have, let's say, the cubic root of x minus 1 is equal to 4. Okay, now we don't have an even root, we have an odd root, so the principal square root rule will not apply. So I have with the cubic root of x minus 1, I can take care of the radical by taking the power that matches what's referred to as the index number of the radical. So here, I'm going to take both sides and raise to the third power. So for the cubic root of x minus 1 raised to the third, think of it like index number and the exponent. They will cancel each other out and remove the radical completely. And like 8 squared, we got 4 to the third is equal to 64. And for x minus 1 equal to 64, add 1 to both sides, and we have the x is equal to 65. Okay, and the cubic root of 65 minus 1 is 64, and the cubic root of 64 comes out to 4. Again, since 4 times 4 times 4 is at 64. And now, for what we have in the case of radical expressions, I'm going to give you just kind of a quick one. If I have that the square root of x plus 5 is equal to negative 7. Guess what? Type of radical we have is a square root. And again, the principal square root rule states that the square root or any even root of an expression cannot reduce to a negative constant. And guess what? For what we have here, because of that part, and because we have an even root radical, we have no solution. And that's going to be because of the principal square root rule. Okay, and I'll just sort of abbreviate that with PSR rule. All right. And so just to kind of kick things off, okay, see if we have any solutions. Okay, so in terms of determining the solution, if any, of x, let's say in the first, okay, let's say that we have the square root of x plus 5 is equal to 4. And then we'll say that we have the cubic root of x plus 7 is equal to negative 4. Now, say we have the square root of 2x plus 5 is equal to 9. And then we'll say we have the square root of x minus 17 is equal to negative 7. And then we'll say we have the cubic root of x minus 17 is equal to negative 2. Okay, for what we have among these 5 equations, okay, we have, first of all, have the square root of x plus 5 is equal to 4. And again, so we have an even root with the square root, and we have the square root of an expression that is set equal to positive 4. And since 4 is not negative in this case, there is a solution. And looking at what we have with the square root of x plus 5 equal to 4, if I take care of the radical, and again, the nature of the radical is a square root. Okay, so if I look at squaring both sides, okay, so the square root of x plus 5 squared, again, the exponent and the radical take care of each other. And we have x plus 5 is equal to 4 squared, which is 16. And so we have for the solution in x, okay, this will be 11. And you can check, 11 plus 5 is 16. Square root of 16 comes out to 4. Okay, for what we have in the next item, okay, we have the cubic root of x plus 7 is equal to negative 4. Okay, now if I had like the square root of x plus 5 or the square root of x plus 7 equal to negative 4, it would be on the basis of the principal square root rule that we would have no solution since an even root of an expression cannot reduce to a negative constant. However, the principal square root rule does not apply to odd root values like cubic roots, fifth roots, seventh roots. The PSR rule does not apply. So we can proceed. So we have with the cubic root of x plus 7 equal to negative 4. I can take care of the radical and free up the x expression upon cubing both sides. So we have here, left-hand side, so this will become x plus 7. And for negative 4 cubed, so you have negative 4 times itself times itself. Negative 4 times negative 4 is 16. 16 times negative 4 is minus 64. And with x plus 7 equal to negative 64, we're going to have 4x upon subtracting 7 on both sides. It turns out that x is equal to minus 71. Alright, and we have with the next item, okay, so you have the square root of 2x plus 5 is equal to 9. Okay, so you have an even root radical expression, and 9 is non-negative, so we can have a solution. And again, just like with x plus 5 earlier, I'm going to free up 2x plus 5 from the square root upon squaring both sides. So left-hand side, okay, so this will become 2x plus 5 is equal to 9 squared, which is going to be 81. And we have upon isolating the x term, so if I take 5 away from both sides, okay, so we have that 2x is equal to 76. So for the missing value x, okay, that is going to be 38. Okay, so here we have 2 times 38, again is 76 plus 5 is 81. Square root of 81 is equal to 9. Okay. Now, for what we have in the fourth item, now we have the square root of x minus 17 is equal to negative 7. And for this we have an even root radical expression, and we have set equal to a negative constant. That's because of the principal square root rule that we have no solution. If we had a positive 7 instead, there would be at least one solution for x. But in this particular case, on the basis of the regulations called forth, okay, with the principal square root rule, we have no solution. Okay, but now, in the case of odd roots, again, they're not affected by the principal square root rule. So we have for this last problem, we can proceed with this one. So for the cubic root of x minus 17 equal to negative 2, I can cube both sides of the equation. And so taking what we have now, okay, left hand side we have x minus 17. Negative 2 to the third, you have negative 2 times itself, so this will give you negative 8. And upon isolating x, if I add 17 to both sides, so we're going to have for the solution in x, that's going to be equal to negative 8 plus 17. So we have for the result here is going to be the value 9. Okay, now, and let's say that if I have a little different dynamic, okay, that is created in working with the variable x, and let's say that, I'll show you just a couple of ways. Let's say if you have a radical being multiplied by a numerical coefficient. Okay, I'm going to show you a couple of ways with one of these problems. Okay, let's say we have something like 4 times the square root of x plus 1 is equal to 7. So you got 4 times the square root of x plus 1 is equal to 7. Now, there are a couple of ways you can go about this. You can isolate the radical. So we have the square root of x plus 1. If we divide both sides of the equation by 4, and so we have that the square root of x plus 1 is equal to 7/4. Okay, now we got an even root expression and we have a positive constant, so there's going to be a solution on this one. And if I square both sides, so I have square root of x plus 1 squared, so this will leave us with x plus 1. Now for 7/4 quantity squared, so 7 squared is 49, and 4 squared is 16. So you have the x equal to 49/16 minus 1. Again, just a little reminder, so we have like 49/16 minus 1. So think like 1 is equal to 1/1. And if I write in terms of sixteenths, okay, so for that difference, okay, this will come out to 33/16. Okay, so there's one solution for x in this one, and this is going to be with the positive non-integer fraction 33/16. So this is one approach, but now for the other one, and I think I like the other approach more. Another way of going about this is that if you have 4 times, okay, the square root of x plus 1 is equal to 7. And let's say if you just don't want to deal with fractions, especially those that do not reduce to whole numbers, what you can do is instead is that you can go ahead and square both sides. Just a moment. Oh, here we go. Okay, so if we square both sides, I like this route more, okay, and you had to be careful. If I square both sides, okay, if I square both sides, now for what I have on the left, now both 4 and the square root of x plus 1 will be squared. However, 4 squared is 16, and the square root of x plus 1 squared is going to be x plus 1. Now we have squared the factors, but we still have a layer of multiplication to deal with. 7 squared comes out to 49. Okay, so 4 squared is 16, square root of x plus 1 squared is x plus 1. Now the result here is not going to be 16x plus 1. It'll be 16 times the quantity of x plus 1. So this will be 16x plus 16 is equal to 49. And this time taking 16 away from both sides. Okay, so we're going to have that 16x is equal to 33 And if you notice with division by 16, we come out to the same result. Once again, where we have that x is equal to 33/16. Okay, so you have at least a couple approaches with this kind of problem. And I try to avoid fractions as much as I can. And you can, but just be careful with the squaring. We have a leading coefficient in front of the radical, and do not make the careless mistake, and the careless mistake would be forgetting to distribute, like in this case, 16 over all of x plus 1. And this is where we have a numerical coefficient in front of the radical. And let me give you another example. Let's say if you have a couple of x terms, one inside the radical as well as one that is outside. And let's say that if we have something like okay, now this is going to be a case where you have apparent solutions that may or may not check out. Here we have x is equal to the square root of 2x plus 3. And if I go ahead and square both sides, so for what I have x squared to the left and to the right. Okay, so I have 2x plus 3. Now I have a quadratic equation that is set up. And if I rewrite in standard form, so I'm going to remove the 2x and the 3 by subtracting. Okay, so I have x squared minus 2x minus 3 is equal to 0. Okay. All right, so looking at what we've got now. For x squared minus 2x minus 3. So we have with our factors, we have the quantity of x plus 1 times that of x minus 3 is equal to 0. And upon using the zero product property, if x plus 1 is equal to 0, now we have that x is equal to minus 1. If, on the other hand, we have x minus 3 is equal to 0, we have that x is equal to 3. Now, in terms of what I mean by apparent solutions, you don't have to write this out, but if I were to check these values, if I check x equal to negative 1, again I have starting out with the equation x equal to the square root 2x plus 3. So if I insert negative 1 for x, so I have negative 1 is equal to, now 2 times negative 1 is negative 2 plus 3. Negative 2 plus 3 is a positive 1. And guess what? Square root of 1 is only going to be at 1. So negative 1 does not check out. And if I check x equal to 3, same equation, different value in x to test out. Okay, so x is at 3. And square root of 2x plus 3, this would be the square root of 2 times 3 plus 3. And 2 times 3 is 6 plus 3. 6 plus 3 is 9. Guess what? To the left I have 3. And the square root of 9 is also at 3. So this is going to ring true. So x equals 3 checks out. And so we have, we could have had up to 2 solutions for x. But for this particular equation, only 3 is going to fit the bill in terms of satisfying all the criteria that we have in this case. All right. And just for the next few moments, I'll say that for the remaining portions. Tell you what, let's see what we get in solving for x. And we'll say that we have 5 times the square root of x minus 3 and we'll say that in this one, we'll say 5 times the square root of x minus 3 is equal to 7. And we have also solving for x, whereupon we have that x is equal to the square root of 4x plus 12. Okay. So let's see what we get for x in both of these radical equations. Okay, for these two problems, okay, we are involving the use of square roots. Okay, so for both of these, in a sense, the principal square root rule is going to have to be complied with. Okay, so we have, in the first item, we have 5 times the square root of x minus 3 is equal to 7. And again, we have the square root of an expression cannot reduce to a negative constant. And had you divided by 5 from the get-go, you have like the square root of x minus 3 would reduce to positive 7/5. Okay, so there would be a solution in x. And you can divide both sides of the equation by 5. That is one option. Here, what I'm going to do instead is just go ahead and square both sides with the 5 still attached to the square root of x minus 3. So looking at squaring both sides. Okay, so again, squaring both sides, so you have 5 squared is going to be 25. Square root of x minus 3 squared, okay, you have x minus 3. Okay, so again, let me mention this. Okay, squaring the left-hand side, it raises both factors to their equivalence in squaring, okay, but it does not automatically take care of the multiplication. We still have that bit of added exercise to apply. Now for what we have to the right, we have 7 squared. Okay, that is going to be 49. Okay, so after squaring both sides, left-hand side had the distribution of 25 all over x minus 3. So we're going to have not 25x minus 3, but 25x minus 75. And here we have two-step linear equation. So you have 25x. Again, minus 75 is equal to 49. And if I get the x term by itself, so I have upon adding 75 to both sides, we have 25x is equal to, let's see, that's going to be 124. And we have with division by 25, okay, we'll have for x this will be equal to 124 over 25. And this ratio is already in simplest form. Okay, so your missing value for x, you have a 124 25ths. All right. Now for what we have in the case of the next item, we have, again, x present on both sides of the equation. Okay, we have one x outside the radical, one x inside as part of the interior expression with the binomial 4x plus 12. And so for what I have in this case, I actually have x equal to the square root of 4x plus 12. And if I take care of the radical, I can just square both sides. Okay, so we have x squared is equal to 4x plus 12. So I have a quadratic equation, and if I take what I have and put into standard form, so I'm going to set this equation to 0. Okay, by taking away 4x and also subtracting 12. So we have x squared minus 4x minus 12 is equal to 0. And looking at factoring, so with x squared we have x and x. Factors negative 12 with a minus 4 sum or difference. Okay, so we have more weight given to the subtracting than to the adding. Okay, so we have the quantity of x plus 2 times that of x minus 6 is equal to 0. And again, utilizing the zero product property, we have setting x plus 2 equal to 0. We have x is equal to negative 2. With x minus 6 set equal to 0, we have another apparent solution with 6. Okay, so we might have two solutions, we might have only one solution, or we might not have any at all. Okay, so if I check what I have here with x equal to negative 2, so just plugging in. Okay, so x is at negative 2. To the right, so I have the square root of 4 times negative 2 plus 12. 4 times negative 2 is negative 8 plus 12, and so negative 8 plus 12 is going to be 4. And guess what? We have negative 2 to the left. However, for the square root of 4, square root of 4 cannot reduce to a negative constant. And negative and positive 2 cannot be equal to each other, so right away x equals negative 2 does not pan out. Now for x equal to 6, okay, so with x at 6, so 6 is equal to the square root, and we have 4 times 6 plus 12. And 4 times 6 is 24, plus 12. 24 plus 12 is 36, and the square root of 36 is 6. Okay, so we have 6 is equal to 6. That is true. So where negative 2 comes up short, we have x equal to 6 to end up meeting all the requirements. So it comes through all parameters and does check out. So we have one solution for this particular case, and that is with the number 6. All right, and now just some items to mention. Again, the Alex first homework, okay, that would be due tomorrow night at 11:59 p.m. And in terms of looking at radical equations, from page 70, just go ahead and be looking into numbers 103, through 108, and also number 110.